Space Telescope. So you're standing outside the control center. So what I'm going to do is give you some fun stuff, but you're social people, right? The first kids on the, but and don't tweet this until Monday. Okay, promise me, right? But there'll be a new Facebook account as well by Monday. Okay?
Was it a big announcement coming Monday?
No discovery. It's a big announcement. It'll have a lot of great stuff on it. So I just want to let you be aware of it. Okay? So what I have for you here is some highlight books around. So these basically, all right, one more here. I'm also going to give you guys 3D bookmarks. So you'll be the only kid on the block with your own 3D bookmark. Okay?
I'll take the extras.
So, okay. So all that being said, I'm going to give you I'm going to let you actually go in the control center with me in a moment. But what I want to do is just kind of give you some background information. All right. So this is a picture that was taken of Hubble by the astronauts one of the last times they saw Hubble. This was back in May of 2009. And this is a small sliver of, so if you take all the water out of the swimming pool and you look down at the bottom, you'll see those black swim lanes, and they're perfectly straight. But as soon as you put water in that swimming pool, those lines do this. Because as the light comes up from those lines, it gets refracted by the water. And that's the same thing that happens to objects in the sky as the light comes down and tries to hit telescopes. So we put Hubble up. It's about 340 miles above the Earth's surface, so it doesn't have that problem. It also allows us to see different wavelengths of light, and we're going to talk about that in a minute. But this is a scaled model of Hubble. It's 1/5 scale. The actual one is 43 feet long by 14 feet wide and weighs approximately 27,000 pounds. So it's the size of a school bus. The way Hubble works is you have a curved mirror here, the primary mirror. It's 8 feet wide. And that mirror was ground so smoothly that if we expanded it to be the diameter of the Earth, you would never find a bump that's higher than 6 inches tall. So the light comes down and hits that mirror from your target. Because it's concave, it starts to move it toward a focal point. There's a secondary mirror here that's convex, that's 1 foot wide. It starts to move it down further through a hole in the center until it hits instruments. It either goes directly into the instruments or it goes to the side to other instruments with a pick-off mirror, 45-degree angle that takes it 90 degrees to the side. Now the bottom instruments are about the size of a refrigerator, a large refrigerator. They weigh about 800 to 1,000 pounds each. And the outside instruments, which go around, the outside are wedge-shaped. So they're basically the size of a mini grand piano. And they weigh, 3 of them weigh 400, 500 pounds each. The other one weighs about 900 pounds and is our primary camera. Now the kind of instruments that we have on board, for the most part, are cameras and spectrographs. So what a camera does is obviously it takes a picture. What a spectrograph does is it breaks the light into a rainbow. And if you take a look at like the sunlight, if you broke it into a rainbow with a prism and look very closely, you would actually see 600 black lines in it, like a barcode. And the kicker is that every element in the universe has its own barcode. And so you can then take a look at those lines, where they're at, and you can determine what elements that particular object is made of. If those lines are shifted from where you think they're supposed to be toward the red side of the spectrum, then it's redshifted. And then we know that the object is moving away from you, and you can compute the speed it's moving away from you. If it's blue shifted toward the blue side of the spectrum, then you know it's moving toward you, and you can compute the speed. You can also do other things with the spectrographs. You can determine temperature and pressure. There's all kinds of information. So spectrographs are just as important as pictures. In fact, they give you more insight into the characteristics of that object often than a picture can. The other 3 instruments that go around the side, they're interferometers. Now, that's a big word. You don't have to worry about understanding it. But the key is what they do is they help me get to a target, focus on a target, and lock on a target. So the way this works is, you have your cameras open, and if you want to take a picture, say, of that object or of Hubble, you're going to basically put it in the middle of your field of view, and then you're going to snap a picture. Unfortunately, we don't have a real-time field of view on Hubble. So what you're going to do is you're going to give me 2 guide stars. You're going to put a guide star below it, and you're going to pick a very specific guide star to the right of it, as an example. And I'm going to take 2 of those interferometers that are called fine guidance sensors, and I'm going to find those guide stars with them and lock onto them. And if they're locked on, then I know that's got to be smack in the field of view of my camera. And that's how we determine where we're pointed to take a picture. Now the kicker is, we often take pictures of things that are very far away. So for example, we'll take something that's 13 billion light years away. Now a light year is 6 trillion miles. So when we're taking pictures of galaxies that are that far away, they're only a few pixels. So what happens if I do this with my camera while I'm taking a picture? It gets blurry. So we can't do that. So we have a requirement that says that we have to be very, very steady when we take a picture. That requirement can be best explained as if you kind of tape a laser pointer on the side of Hubble, and Hubble was here in Washington, D.C. area. The requirement is that those fine guidance sensors stay locked on the star and don't move off that star, such that that laser pointer can point on the head of the president on the dime. So Franklin Delano Roosevelt, his head, it has to stay on that head the entire time I'm taking a picture for up to 24 hours. The kicker is that if Hubble's in Washington, D.C. here, that dime is over 200 miles away on the Empire State Building in New York. So that's the pointing requirement that we have, and those fine guidance sensors allow us to achieve that. The way we turn Hubble is with something called reaction wheels. We use the law of Newton. For every action there is
an equal and opposite reaction.
Correct. So if I turn the wheel to the right, Hubble will turn to the left. So we have 4 of those wheels, and they spin Hubble about the speed of a minute hand, so I could turn 90 degrees in about 15 minutes. But they're not enough. And the reason they're not enough is because even though I said, hey, we're above the atmosphere, there's still air up there. And that air it's not enough for us to breathe, but it causes atmospheric drag, and it can cause torques. As I'm trying to take a picture like this, those big solar panels and the body of the spacecraft itself has torques coming across it. Maybe it's a solar wind causing some of those, whatever, but it's a force that's causing it to turn in different directions when I'm trying to stay pointed steady. So what we do is we either have to spin our wheels even faster to compensate for those forces, but those forces build up over time, and I can't spin the wheels fast enough. So what we use are these bars here. These are 8-foot long bars, 3 inches wide. They have coils wrapped around them, and when I fire them up with electricity, they become magnets, and they use the Earth's magnetic field to pull and push Hubble in a different direction to get rid of those extra forces. Okay, so that's kind of a general background. Let me just talk to you 1 second about this particular picture before we head in. This is a picture of the Eagle Nebula. Nebula is the gas and dust that's left over from a star that was supernova many years ago. It's about 6,500 light years away, and this tower on the left is about 5 light years tall, so 30 trillion miles, per se. It's one of the most famous pictures ever taken by Hubble, and I say it's the most famous because Time magazine included it in its top 100 pictures ever taken by humans. So the reason it's famous are these little fingertips here. These are balls of gas and dust that are accumulating, and as they accumulate, they get more gravity, they pull in more and more gas and dust, and if it gets big enough and there's enough temperature and pressure in the middle, a nuclear fusion reaction starts and a new star is born out of the gas and dust that's left over from a dead star, poking out from here. So this was the first time that we had seen starburst up close and personal. Now, if you recall, I said to you, one of the other advantages of being up in space is we can see different wavelengths. So the ozone layer blocks ultraviolet light, some ultraviolet light from hitting the ground, and that's important to us because it helps prevent us from getting skin cancer, as an example. But astronomers want to see that light because different wavelengths of light tells you different things. It also blocks. This is a picture taken in visible light, like your eyes, an infrared camera of the same object. So you can see tens of thousands of stars that are behind this dust cloud that otherwise you would never have knowledge existed because you're looking at different wavelengths. And that's why astronomers want to see those different wavelengths, and the advantage of putting a spacecraft and telescope up above the Earth's atmosphere. Okay, so we're going to head in down the hall. Okay, so before we go in, this is a test. What's that one word? Okay, so let's head in.
Thank you. Thank you.
Okay, so you all want to gather around. Okay.
Sorry.
Can I ask you a photo booth question real quick?
Sure.
I'm noticing the cross-hatching on the stars. Are they shooting with a really narrow aperture? When they
This?
referring back to the photos on the wall.
Well, that's the same thing as here. So
Yeah, that too.
So
Mhm.
when you look at seeing these, you can tell which are the stars in this picture. Why don't you guys keep moving down with it? Don't hesitate to get in front of each other, okay? Because you want to see this image. This is the key, okay? Okay, so the question is, why are there these crosshairs in stars? And you can tell these are stars because they have the crosshairs. That's called a diffraction spike. And you get the same thing when you're looking at taking pictures sometimes through your backyard telescopes. The reason for that is there's a secondary mirror, and that secondary mirror is held in place with 4 rods. 1, 2, 3, 4. And the light is reflecting from the star off those rods. It's this, on a backyard telescope, that's called a spider. Your secondary mirror is held in place with a spider. And that's why you see diffraction spikes in the stars. And that's key to this picture because everything, this was a part of the sky that we took a very long exposure on. It was over 1 million seconds. And everything in this picture, with the exception of these foreground stars that you can tell which are the this crosshair pattern, there's about 7 of them, I think. 1, 2, 3, 4, 5, and 6, and there's a 7th one somewhere. Everything else in this picture is a galaxy. So it's like our Milky Way. So it's hundreds of billions of stars all rotating around some central point in typically a black hole. But the idea is that there are 10,000 galaxies in this picture. Every little dot, no matter how small it is a galaxy. And so this gives us an idea how populated the sky is and how populated the universe is, because this is equivalent to looking through the eye of a needle held at arm's length. So if you do the math, and there's about 10,000 galaxies in here, and you figure out how much of the sky this is, and you make an assumption that no matter where you look in the sky, it's pretty much the same thing, and that's what we found so far, then you'll realize that there's probably about 200 billion galaxies in the universe. And then, of course, each of those have hundreds of billions of stars, so what are the chances that there might be life somewhere else out there, especially now that astronomers believe that probably around almost all stars there's at least one planet. Okay, so this is called the Hubble Ultra Deep Field. I argue it's the second most famous picture we've ever taken. Okay, so let's head down here. Okay, you want to make sure you can see in this window. And I'm okay. Okay, make sure you gather around and see in the window, please. Okay, so this is the room, and you guys can keep moving down a little bit more if you can. Okay, this is the room from which we control Hubble from. Okay, so the way this works is that we go out once a year and call for proposals from scientists around the world. Anybody can put in for Hubble time. We pull together a group of scientists that are about 140 or more. We break them into expertise areas, galaxies, solar system, exoplanets, you name it, and they evaluate the proposals. Typically, you have about a 1 in 5 chance of getting your proposal selected. There's only so many hours that we can take a picture a day, and that's part of the reason why not everybody can get their proposal selected. Not because they're not good, but there's only the top of the top can get enough time to be able to do this. Once they're selected, they're scheduled. And then a command load is brought down to us that we upload to Hubble. Okay, it gets uploaded on that black box there. That's equivalent in the window. That big black box is equivalent to the computer that's on board. That computer is, we're going to see how many people know this. That's a 486 chip. Okay. So I'm going to just quickly compare that for you. It gets about 24 hours worth of command. I'm going to compare that to an iPhone 7. I don't have the specs on the iPhone 8, so I apologize. So in that computer, there's actually a primary and 2 backup computers, all right? But we only use one of them at a time. So in your iPhone 7, you have I believe it's an A8 Fusion chip that has 4 processors in it that run simultaneously at 2.3 billion cycles a second. This 486 chip runs at 25 million cycles per second, and of course only has 1 chip. Okay. This has 2 gigabytes of RAM for you to load your operating system and your apps to run them, etc. That has 2 megabytes. This has, you can either get it, what, 64, 128, or 260, whatever gig of memory for you to save your songs and your pictures and your movies and all that. That has 1 megabyte. So we don't even save the science images to it. We save the science images to a separate recorder. But that power is all we needed. It's actually an upgrade from the original computer that was on board, which only had 64K of memory. All right, but that we only use about 60% of its computing capacity and about 70% of its memory, and it allows us to do all kinds of things. So what they're doing in this room is that they monitor the spacecraft to make sure everything's working properly, nothing's getting too hot, nothing's getting too cold, the voltage levels are right, it's responding to commands as we execute them, and making sure that there's just nothing else going on we aren't aware of. Now there's a plot on the screen on the right, the printout on the right there shows you what a typical screen would look like. On the left, that's called a mission schedule, and we print that out every day. Those are other things we worry about. We worry about when it's in day or night so we can charge the batteries properly. We worry about when it's in the SAA, South Atlantic Anomaly. That's an area of high electrocontamination above the South Atlantic, for which we have to actually power down some of our detectors so they don't get damaged.
Is it the Bermuda Triangle?
No, nothing to do with the Bermuda Triangle, sorry. Then we worry about the instruments, and then of course all the communication contacts, and there's different types of communication contacts, whether we're uploading commands or downloading science data. So they worry about all that there. Now the reason that there's probably nobody in there, I can't see, but my guess is there's nobody in there, is not because they're all AWOL, okay, but about 2011 we went to automated operations. All right, so now because we put that new computer on board, we were able to do a lot of self-monitoring by the spacecraft itself. So now the spacecraft can check itself if things are getting too hot or too cold, and it'll send an error message down. The ground system checks for trends and that, and so it'll generate an error message, and if there's any kind of error message, it'll send a text message to us, to our iPhones. Now, we have so many minutes, it's actually, there's specific people, depending, that it texts. They have so many minutes to respond. If they don't, then the ground system assumes that they turned their phone off, or it's in the car and they went grocery shopping, but it needs to talk to somebody. So then it goes to the next person and to the next person until it gets a response. Once it gets a response, we're able to look at some of our telemetry, some of our data with our iPhones, wherever we're at, just to get an idea of what's going on and whether we need to come in. Sometimes it's serious, we need to come in. Other times it's just the end of a communication contact fell off, so we don't have to worry about it. We'll just pick it up the next time. So it all depends. All right, so now we are an 8x5 shop, meaning 8 hours a day, 5 days a week, and we can go home on the weekends and for holidays and at night. Where before we were a 24/7 shop. All right. Okay, so why don't we head around the corner? Okay, so this is another room that we have. It's more general purpose. If there's there's areas for each discipline, such as electrical engineers and point and control system engineers and flight software people, etc. If there's an anomaly, all the people can come in here. They all have their own screens. They can bring up whatever data they want to see to understand what's going on, help figure out what's going on. We also use it for testing purposes. So we have a large simulator, high fidelity simulator in another building. And before we do anything on the spacecraft, we always test it against that simulator to make sure it works properly so we don't accidentally do something that we do not want it to do. The other thing that we use it for are things that we don't have automated. So for example, flight software. If we have a new version of flight software we want to upload to that computer, what do? We end up having to make sure that it gets uploaded properly, it gets installed properly, it gets invoked properly, and it gets saved to EEPROM properly. So all that kind of thing we have to do by hand. So we bring people in and they man their stations to make sure that that all works properly. Okay. So one of the other things that I wanted to show you here was some of these display cases. These are things that we brought back from the spacecraft, or tools that the astronauts used when they worked on Hubble. The astronauts went up 5 different times on what we call servicing missions on board the space shuttle to either fix things on Hubble or upgrade the instruments on Hubble, whatever needed to be done. So this is an example here of a power supply for one of those refrigerator-sized instruments. So you can see the picture here of the refrigerator-sized instrument. What happened was the power supply went, so the instrument no longer worked. So we had the astronauts switch it out. They brought it home. So this is what the card looked like in this picture before we took it apart to figure out why it failed. These are small converter boxes that we pulled off to analyze them. They basically take power down from one voltage level to another, allow us to use it in the instrument. If you notice, there's a lid here we took off, and it has the red dots. It's kind of like glue. And if you look closely, if I flipped it over, it matches the red dots here to help kind of glue the lid down. What happened was when we launched, there was air inside of that, and the air expanded and kind of buckled up the lid. That lid pulled on the circuits, and after 7 years, that stress caused a solder joint to fail and a power converter fail. And then, therefore, the power supply didn't work anymore. So we wanted to change it out, have the astronauts change it out. So we created for the astronauts this particular tool here. It's called a card insertion extraction tool. And the purpose behind that is 2 things. One is safety, and the other is efficiency. So the safety part is that we don't want the astronauts touching the card. It has sharp points on it, so we don't want them to accidentally puncture a hole in their glove. That would be catastrophic. And we also don't want them to accidentally break something on the card, so now it doesn't work and it's useless on the new card. What we did was we had them do this particular device. You can see there's a big knob on the back for the claw that grabs it. And then there's telescopic legs. There's silver telescopic legs that when you turn this handle, they come out. So the way this works is if this was the instrument and I laid it on its side, okay, and this is the card, I take the claw and I put the claw on there, and as I extend out the legs, it pulls the card out. I put the new card in, and then as I retract the legs, it pushes it back down in, such that all the pins are perfectly aligned. They go in the first try. That gives me efficiency. Okay, it's important to have efficiency because when the astronauts go out on a spacewalk, that we call EVAs, extravehicular activities, we only get 6 hours with them. Okay, if you think about it, before they ever go out on the spacewalk, they have to get in their suit. They've had to eat breakfast, etc. But they have to get now in their suit. They have to get in the airlock. They have to depress and everything. So they're there a couple hours before they even go out. Once they go out, for 6 hours, they don't get to nap, and they don't get to eat because of a choking hazard. They can drink water. They have a tube that they can suck on to drink water. So it's very important to get everything done as efficiently as possible because they're basically running a marathon for 6 hours. Because unless they're one of the lucky ones, which they have their feet in the foot constraints that are restraints that we have for various parts of the activities they do, they're floating around, and every time they push one direction, their body wants to go in the other direction. So they're fighting that the whole time that they're out there. So they're exhausted when they come in. So they want to keep it as efficient as possible. So these kind of tools allow us to make the tasks go as quickly as they can, work the first time, and that allows us not only to get them in earlier, but allows us to get more things in that we want to get done on the spacecraft in that 6 hours. Okay? Okay, so I want to take you over here, and I want everybody to kind of gather around this particular screen. Okay? Okay, so this, for those people who haven't seen one, this is a CCD chip. This is a charged coupled device. This is the same thing that you have in your camera on your phone. Okay, and Hubble, has done a lot of advances in the area of CCDs. This is, if you think about it, Hubble. What happens? Let me ask you this question: what happens every time you go and you buy a new phone? What happens with the camera?
It gets better.
It gets better. And how does it get better?
The technology is just
The resolution.
The resolution, okay? So you always get more pixels, more megapixels, right? So Hubble's no different. The first camera that went up there that took a lot of the famous pictures was a 2.6 megapixel camera, all right? We installed this one. Now, this is a duplicate of the chips. There's actually 2 chips there that we put back to back to make one detector. We actually increased it from 2.6 megapixels to 16 megapixels with this particular chip, which allows us to see at a much higher resolution when we take pictures. So just like your cameras continue to upgrade, Hubble's cameras continue to upgrade. And just so you know, if I remember correctly, the first commercial digital camera, digital SLR that came out 1 year and before we launched this 16 megapixel camera. And that was a 1 megapixel camera, and it sold for $10,000. So these didn't become available at this resolution to the consumer for many, many years after that. So Hubble has been pushing that technology to increase it so that we could bring back more science as much as we could. Okay, this guy I want you to see real quick. This is a tape recorder. For those of you who've never seen a tape recorder, it's kind of scary, from my perspective only, not from yours. But this is how we used to record data. So there were 3 of these on board when we launched Hubble. This was one of them. We brought it back in 1997. If you notice, there's a little yellow sticky on there with an arrow on it. That arrow points to where the tape came off the white spool. You can see that. Again, you guys can get close. You don't have to be shy, so you can see stuff, okay? And of course, the good news is that happened on the ground when we put it in our simulator over in another building. If it happened in space, then the tape recorder would be no good, and we would be out of one capability of storing science data. So we replaced these over time, 2 of them, with solid-state recorders. That's equivalent to your USB stick, right? But it's about this big. And the reason for that is manyfold. Number 1 is it doesn't have any moving parts for it to break, like in that particular case. Number 2, it holds 10 times as much data. That becomes critical when I go from a 2.4 megapixel or 2.6 megapixel camera to a 16 megapixel camera. You know how big your files are now. So we want to increase, that storage capacity now to handle the new cameras. And it also allows you to read and write at the same time and read and write faster than you can with the tape recorder. So there were all kinds of reasons to upgrade. Okay, so this particular device is a gyro, okay? The gyro is a device that allows you to turn the spacecraft, actually measures your turning the spacecraft so you know exactly which direction you're turning and what speed you're turning at. And these are important for us to be able to understand how we're turning when we go from target to target. So we have 6 of those on board. We use 3 of them at a time. 1 has died since our last servicing mission, so we have 5 left. And the problem became during the first servicing mission back in 1993 that we weren't sure if there was a problem with the gyro or if there was a problem with the control box, electronic control box for the gyro. So we brought both of them back, and we analyzed both of them, and we realized that this guy had a bad capacitor. So we've changed that out, and we brought it back up to flight status so that way if any of the other boxes that were up there that control the other gyros had a problem, we could switch them out, but none of them have. Hubble was launched in 1990. They're 27 years old, and they're still working fine.
Hooray.
Okay? Okay, so that's all I have to tell you today. Does anybody have any questions before we head back to the lobby?
Other than mechanical failures, what's the known ending reason for the mission eventually?
Well, we don't know.
Okay, we don't know. I mean, but other than mechanical, is there fuel or is there something?
There's no fuel on Hubble, so that's number 1. There are solar panels and batteries, and those degrade over time, but we think the last pair of batteries we had lasted us 19 years, so we think we're pretty good there. You have atmospheric drag, which is lowering Hubble, so Hubble could re-enter. Although our latest predictions are they probably wouldn't re-enter if you just had normal solar cycles. You probably wouldn't re-enter until the late 2030s. So the other one would be mechanical failures.
Okay.
Okay. Yes?
How do you feel about James Webb coming online soon?
Excited. Okay, so let's just make sure everybody understands. Hubble doesn't go away because James Webb comes along, because James Webb is looking at a different type of light. It's looking much further into the infrared spectrum. So the scientists want to see what they see with a particular object. They also want to see what Hubble sees with that same particular object, because we're seeing it in ultraviolet light, we're seeing it in visible light, and those two things James Webb can only see a little bit of or none of. So the scientists want both telescopes to be around for as long as they can, so they can take simultaneous images of these multiple objects and get as much information as they can in the different wavelengths of light. So we're very excited. I think James Webb holds the promise of being another Hubble in terms of expanding our knowledge, because it'll be able to see much further into space, or further back in time, shall I say, because the objects that are further and further away their light is redshifted, and it's moving faster and faster away from us, so the only way to see that is with a high-powered infrared telescope like James Webb. Okay. Any other questions? Okay, well, why don't we head back to the lobby then? Thank you very much. No problem. Well, we try to accommodate whenever we can.
I just did a lesson like students on Hubble when we did a Hubble models out of paper tubes.
I like it. So we were enjoying Halloween, because of the different Halloween Hubble costumes and
Oh, I saw some of those.
so and then if you saw the one of the pumpkin, that's my daughter. Poor artist side out of her. Oh, that kind of box. Okay.